In this lesson we are going to learn about counting techniques. We are going to see how we can count how many elements there are in a set. This is important in probability theory because as we have seen in the previous lesson, the probability of an event when its outcomes are equally likely to happen will be the number of elements in the event divided by the number of elements in the sample space. We write this down so to remember it. So we have that the probability of an event A will be the number of elements in A divided by the number of elements in S. Sometimes it is not very easy to know how many elements there are in the event A, and that's why we're going to see techniques so we can calculate the number of elements. So today we are going to see counting techniques. We are going to see the fundamental principle of counting, arrangements, combinations, and finally different examples which use all these three techniques. So let's start by giving an example. Our first example, we have a machine which consists of three components, C1, C2, and C3. We denote the three components by these three letters. Now, each component either works properly or not. And we are interested to find out how many different outcomes there are in our sample space. We see here that we may be interested when each component is going to work, because the machine may not work when all three components do not work properly. So we have, sometimes we would need to calculate, for example, the probability that all three components will work properly. We go back to our example, and using graphical methods we see that the machine has component C1 which will work properly. We denote by yes, by the letter Y, yes, that the machine works properly, and by N, that the machine does not work properly. The second component, in the second stage, the machine either, the component C2 either works properly or not, and here C2 either works properly or not. For the third component, we see again the same thing. We note here that each component works independently from the other. So C2 does not depend on if C1 works or not. And C3 does not depend on if C2 or C1 works properly. For this example, let's make clear what the sample space is. So we have that S in this case will be all possible outcomes. Will be that the first component will work we denote by y, yes, the first component, if it works or not. Second component works or not. Third component. So we have many possible combinations. Here, all three components work properly. In the case that the first two work properly and the third does not, we have this element, and so on. We write all elements of sample space S. We see that even in this case, when the example is quite simple, writing down all elements in the sample space could be quite difficult, could take time. So we are going to find techniques to count all these elements. So we write down the elements. We have all not working. The second working. The second and the third working. The third only working, and the first and the third working. If we count the elements in S, we see that there are 1, 2, 3, 4, 5, 6, 7, 8 elements. Going back to our table, we see that this graphical method is much easier. We see that if we follow each section in this tree, that we end up in 8 different outcomes. We have working, 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 the 3 components, not working, the third, working, working, and so on. So this is a very easy graphical way to work with this kind of problems. We are going to see another example, another graphical example. Assume that we have 3 particles. Now, every hour, each of these 3 particles will be doubled. So what we have is that we start with 3 elements. Every hour, each element is doubled. So we see that in each step, we can see how many different outcomes we can have. Now, although graphical representation of such problems makes things much easier, even in this example with the particles, we see that if we go on in the 3rd step or 4th step and so on, things become more complicated. It's quite difficult to count by hand the number of possible outcomes. So we are going to use counting techniques. The first one is the fundamental principle of counting. We have that if an experiment can be divided in our sub-experiments, where the first sub-experiment has n1 possible outcomes, the second one has n2 possible outcomes, and so on, the third one n3, and between these outcomes are independent one of another, we have that the total number of outcomes of the experiment will be n equals n1 times n2 times up to nr, the number of elements of the first sub-experiment, the number of elements of the second sub-experiment, and so on, all multiplied together. So back in our previous example, we had that the machine consists of the three components C1, C2, and C3. We know that each component either works properly or not, and we want to find how many different outcomes there are in the sample space. We remember that we have seen by hand that there are 8 different outcomes here, and we are going to use the counting technique to find out how many elements there are. So for this example, the machine consists of 3 components that work independently. This is important. We cannot use this technique when the sub-experiments do not work independently. And we have that C1 has 2 possible outcomes, either works or not. C2 has also 2 possible outcomes, it works or not. And C3 has also 2 possible outcomes, it works or not. It is not necessary that all sub-experiments have the same number of possible outcomes. We can have examples where, for example, the one component either works or it doesn't work very well, let's say, or it doesn't work at all. So it would have 3 stages. Going back to our example, so according to our counting technique, the total number of possible outcomes for this example will be 2 times 2 times 2, which is 8, which agrees with what we found by counting the possible outcomes in our tree. Now, we go to see another technique. We are going to see arrangements. We have that the number of ways that we can arrange n objects if we take r at a time without replacement is n times n minus 1 times we multiply up to the number n minus r plus 1. It is important to note here that the objects which are taken cannot be replaced. We cannot put them back in the n objects. If we do that, the number of outcomes will change, the number of possible outcomes will change, and we are going to see later on when we are going to have such a case. Now, in this case, we are going to think this as we have our boxes, which we draw here. Box 1, 2, 3, and so on, up to R. And we have n objects and we want to fill in these boxes. So we see that we can put each time n different objects. We can put object 1 in the first box, or object 2, or object 3, and so on. So we can put n different objects here. Now, if we have already filled in box 1, in order to fill in box 2, we have left out with n minus 1 objects. So here are n, 1 has already been taken out to fill in this box. So we have n minus 1 different objects to fill in this box. So for box number 3, we are going to have n minus 2 different objects. Going on like this, we see that for the last box, there are left n minus r plus 1 different objects, and thus the different number of outcomes here will be total of this number if we multiply this number. Let's see an example. We consider the 5 integers 1, 2, 3, 4, and 5, and we want to see in how many different ways we can pick up 2-digit numbers without replacement. This is important. For example, we have number 12, 1, 2, number 24, and number 31, and so on. When we say without replacement, we mean that we cannot use the same integer 2 times. So we cannot, for example, have number 22, number 33, and so on. Let's use our technique to find how many 2-digit numbers we can have. So in this case, n is 5, r is 2, we have a total of 5 numbers. We want to pick 2, and so we have 5 times 4 equals 20. The first time we can pick one of these 5. The second time, one will already have been picked, so we are left out with 4. If we draw this using our boxes, we can understand that in this case we only have 2 boxes to be filled in, each one representing the digit in the number, in the 2-digit number, and we have 5 integers from which we can pick a number. So we have 1, 2, 3, 4, and 5. The first box can be filled in by one of these 5 numbers. For example, number 2. The second box now can be filled in with one of the remaining numbers. So in the example, we leave out the number 2, which has already been picked. So there are 1, 2, 3, 4 different ways to pick a number here. For example, number 5. So we have number 25. So there are, as we have seen, 20 different ways of having two-digit numbers using the 5 integers. Let's see another technique. Arrangements. The number of ways we can arrange n objects taken at a time with replacement this time is n to the power of r. Let's see, let's use our boxes again. In this case, as before, we have our boxes. But here we can fill in a box in n different ways, and we replace the object picked back into our group of objects. So here again we have n choices from which we can pick to fill in box number 2. So the difference than before is here that we do not have n minus 1, but we again have n different choices. The same way, for box number 3, we have n different choices, and going on, we see that up to the last box, we can fill it in with, we have n different choices to fill it in. So this number, n times n times n times n, it's r times, it's actually what we have calculated, n to the power of r. Let's go back to see an example using this technique. In this case, we consider again the 5 integers, 1, 2, 3, 4, 5. We want to see how many two-digit numbers we can get, but this time with replacement. So in this case, we are allowed to have number 22, number 33, and of course all others that we had before. We understand that when we are allowed to replace our items, our elements, we are going to have more possible combinations. So when n is 5, r is 2, we can see that we have 5 to the power of 2, 25 possible outcomes. And we see that, as expected, in this case, we have more possible outcomes than in the case when we didn't have replacement. So here there are 25 possible outcomes. Before we had 20 possible outcomes. Combinations. We consider the letters A, B, and C, and we want to see how many different combinations of two letters can we get. Now in this case, from now on, the word combination will be used only when we are interested in the order that the letters will appear. We are not interested in the order that the letters will appear. So for example, AB is the same as BA. In the examples we saw before, we have seen that the number 12, for example, was different than the number 21. So we're interested in picking up 1 first and 2 second, and then 2 first and 1 second. These are 2 two different choices. When we have combinations, we are not interested in the order as we said. Picking A first and B second is the same as picking B first and A second. So, for this example, all different combinations made using these letters, A, B, and C, are actually A, B, A, C, and B, C. We do not include B, A, C, B, and so on. So, in this case, the number of ways of choosing R elements from a set of n elements will be denoted like this, and will be n factorial, as we call this symbol, divided by n minus r factorial times r factorial. Here we say that the symbol, as I have said, is called factorial, and it can be calculated as n factorial equals 1 times 2 times up to n. Let's see an example. So if we want to calculate 5 factorial, what we have is 5 times 4 times 3 times 2 times 1, which is equal to 220. Let's see again an example to see how we can use this formula. So we consider the letters A, B, and C again, and we want to see how many different combinations of two letters can we get. We have seen before, I am going to write down again, this is a very easy example, and we can see that the possible combination are actually AB, AC, and BC. If we have more choices or more elements we want to choose, we understand that the problem becomes even more complicated. So, in this case, what we have is that choose R from N can be done in 3 different ways. 3 factorial divided by n minus r, 3 minus 2 factorial times r factorial. Here in this formula, we are going to work with this a bit to note something, that we had 3 factorial and 3 minus 2 factorial times 2 factorial, which is actually, this part is 3 times 2 times 1, divided by, this is 1 factorial is actually 1, times, this is 2 factorial, 2 times 1. Usually, there are some numbers here that are be cancelling with some numbers here. In this case, we can see that these are cancelled with this, and we can easily see that the result is 3. If these numbers are even bigger, we can understand that cancelling out here will make calculations much easier. Another example is if we want to see in how many different ways we can select a committee of 5 people from 7 men and 8 women. So in total we have 15 people. We want to select a committee of 5. And we want this committee to consist of 3 men and 2 women. We assume that the selection is made randomly. We are not in favor of some person. And we want to find the probability that the committee consists of 3 men and 2 women. We denote this event by A. So, as its selection is equally likely, we know that the probability of A will be equal to the number of committees consisting of 3 men and 2 women divided by the total number of 5-person committees. This is the sample space. This is the total ways we can have, the total number of ways we can have 5 members committee. We don't care if we have 3 men and 2 women. We can have any combination. We can have 5 men, 5 women, and so on. So, in this example, there are in total, we want to choose 5 out of 15 people. So in total, our sample space, we will have 3,003 different groups of 5 people. Let's work through this, see how these are cancelling out these numbers, and that it's easier if we cancel out numbers to make these calculations. So we have 15 factorial divided by 15 minus 5 factorial times 5 factorial. Now this will be 15 times 14 times 13, so on, up to 1. This is 10 times 9 times 8, up to 1. And this is 5 times 4 times 3, up to 1. We can see here that all these numbers, 10 up to 1, will be cancelled out with the numbers here. Let me write more here, 12, 11, 10, up to 1. So you can see all these will be cancelling with this, and we are only left to do the multiplications and the divisions here, which is much easier than calculating all this. Now, for our example, we can choose 3 men out of 7. Be careful here, we have only 7 men. We have to make clear the total number of elements from the group which we are choosing. We are not considering all 15 different choices. We can only choose from the 7. So we have to only use 7 here. So we can choose 3 men out of 7 in 35 different ways. Here we are not interested in which order we choose the 3 men. We are just interested in choosing a particular, these particular 3 people. So that's why we use combinations. Here we've seen that we have 35 ways we can choose 3 men out of 7. And now we calculate in how many different ways we can choose 2 women out of 8. We see here that we can choose 2 women out of 8 in 28 different ways. We can choose out of the 8 possible choices we have, not the 15 we had in total. And we see that we have 28 possible ways doing the calculations of choosing 2 women out of 8. So we can choose 3 men and 2 women. We multiply the number of ways we can choose 3 men with the number of ways we can choose 2 women, and we find that there are 980 ways we can choose 3 men and 2 women from the 15 total number of people. So the probability of our event A, the event A was that we choose a committee of 5 people that consist of 3 men and 2 women, will be 980 divided by 3003. 980 different ways we can choose 3 men and 2 women, and 3003 different ways we can choose 5 people, no matter how many men and women we have in them. So this probability is, doing the calculations here, 0.326. What we have seen in this lesson is counting techniques. We need the counting techniques in order to calculate probabilities, to calculate when we use the rule for the probability when we have equally likely outcomes. We said that we can divide the number of elements in an event by the number of elements in the sample space. And in particular, we have seen the fundamental principle of counting, the arrangements, combinations, and different examples on how to use all these techniques. For more details on this lesson, you can visit the web page of UNINETTUNO Med NetU project.